In this video, we're going to look at question 6 from your paper 1, which is on exponentials and logarithms. Question 6 says, during some research, the size p of a population of insects at time t months after the start of a research is modelled by the following formula, p equals 100 e to the t. Part A says, use this model to answer the following. Find the value of p when t equals 4. So for this question, I've got to substitute t equals 4 into my equation p equals 100 e to the t. Doing this, I get p is equal to 100 e to the power of 4, which I can type into my calculator to give me an answer of 5,460 to 3 significant figures. Part II then asks me to find the value of t when the population is 9,000. So this is find the value of t when p is equal to 9,000. So substituting this in, I get 9,000 is equal to 100 e to the t. Now in order to start solving for the value of t, I'm going to divide both sides by 100, which gives me 90 is equal to e to the t. Now in order to find the value of t, I'm going to use the following rule. If a to the x is equal to n, then log base a of n is equal to x. Now I've got something in a very similar form to a to the x equals n. My 90 is my n, my e is my a, and my t is my x, which means I can write this as ln, which is log base e, of 90 is equal to t. And if I put this into my calculator, ln 90 gives me a value of 4.50 to 3 significant figures. Part B then says it's suspected that a more appropriate model would be the following formula. P equals k a to the t, where k and a are constants. Show that using this model, the graph of log base 10 of p against t would be a straight line. So this means I've got to change p equals k a to the t into a form of y equals mx plus c, where log base 10 of p is my y and x would be my t. So the first thing I'm going to do is take logs of both sides, which gives me log base 10 of p is equal to log base 10 of k a to the t. Now I need to get this t to be an x in y equals mx plus c. So I've got to get it out of this logarithm somehow. So the first thing I'm going to do is use my multiplication law to pull apart my k a to the t. So now I have log base 10 of p is equal to log base 10 of k plus log base 10 of a to the t. Now, because I haven't got two things multiplied by each other inside my log, I'm free to use my power law to bring my t to the front of this logarithm. And I get log base 10 of p is equal to log base 10 of k plus t log base 10 of a. And here, this is in the form y equals mx plus c, where log base 10 of p is my y, log base 10 of k is my c, t is my x, and log base 10 of a is my m. For this next question, just ignore the red that I've got on the graph, because it is for the next question. II says on the grid in the printed answer booklet, draw the line of best fit for the data points t, log base 10 of p, given in the table. So here we were given our values of t and given our values of log base 10 of p. So we just had to plot each of these. So when t is 1, log base 10 of p was 2. When t is 2, log base 10 of p was 2.7. And I did it for t equals 3, t equals 4, and t equals 5. And then I drew my blue line of best fit to try and get through the middle of the points, as close to the points as possible, to reduce any distances between the black points and the blue line. For the next question, you're going to want to make sure that your line of best fit goes all the way to this y-axis. Part 3 says, hence estimate the values of k and a. So as we saw in a previous question, we were able to change p equals k a to the t to log base 10 of p equals log base 10 of k plus t log base 10 of a, where log base 10 of k was my c, my y-intercept, and log base 10 of a was my m, my gradient. So in this graph, I can see that my y-intercept is 1.4, which means log base 10 of k is equal to 1.4. So again, I'm going to use this rule, log base a of n equals x and a to the x equals n. I'm just using it in the opposite way to what I did previously. So this gives me k is equal to 10 to the power of 1.4, which, putting it into my calculator, gives me 25.1 to 3 significant figures. Now I've got to work out my a, and I do that using my gradient. So looking back here, I've drawn a triangle where my change in y is 0.6 and my change in x is 1. This means that my gradient, which was log base 10 of a, is equal to 0.6 divided by 1, which is 0.6. So then I'm going to again use this logarithm rule and get that a is equal to 10 to the power of 0.6, which, putting it into my calculator, gives me 3.98 to 3 significant figures. And there you have the value of k and the value of a, which are estimated off of our line of best fit.